In previous videos, we talked about high-order linear or ordinary differential equations. This time, we will talk about systems of linear ODEs. Recall that a linear ordinary differential equation was something like this. So it's a functional relation between functions of single variable and its derivatives. For example, y second derivative of y plus sine t, y of t is equal to cosine t. A system of ODEs is something like that, like this, when we have more than one unknown function and they're coupled together in this relations in the way shown here. So y prime, the y double prime, they appear in the same equations as x, and x prime appear in the same equations as y, and so on. So more formally, a linear ODE looks like this. We have a differential operator that acts on the function, and it is equal to the right-hand side. And then it's easy to generalize this to a system of ODEs if we upgrade this differential operator to matrix valued differential to the differential operator whose coefficients are matrices. So those capital AN through capital A0, the matrix is the function of t, and we act on the vector function, which it's a column of unknown functions, and it's equal to vector of the right-hand side. So that is exactly the same sort of thing, except now the functions are vector valued. So they take values, they're maps from R to Rn rather than just maps from R to R. And the coefficients are matrix valued functions. So for instance, this system of equations from the previous slide can be written as this differential operator with the 2x2 matrices multiplied by second derivative, first derivative, and just the matrix, acting on xy is equal to vector 10t e to the t. Implicitly in this discussion, we understand that the set of functions is a vector space with a component-wise addition in scalar multiplication. That is, so for example, if you have bold f and bold g are vector valued functions, they're maps from R to R3. So we might write a linear combination of them like this, right? So as if they are vectors in R3. Some, but by no means all, linear transformations of the space of vector valued functions are given by matrix multiplication by matrix valued functions. Say, if you multiply this matrix sine t squared e to the t 4 by the column vector fg, get this vector. Well, why is that? So the systems of ODEs, they arise when several quantities are varying simultaneously and then depend on one another. So for instance, consider a planet of mass m orbiting a star of mass big M. We'll take our coordinates so that the star is fixed and we'll disregard the pull of the planet on the star. Then the planet has coordinates x1, x2, and x3 if the star is the origin. And we can write down the F equals ma equation where acceleration is the second derivative of the position vector like this. So mx double prime of t is equal to negative g Newton product of masses of the star and of the planet vector x divided by absolute value of vector x cubed. So that's a system of three non-linear ordinary differential equations. So as you can see, because of this 1 over absolute value of x cubed on the right-hand side, this coefficient, this function makes the system of equations non-linear. Another example also from physics, we have 3 springs with the stiffness coefficients k1, k2, k3. And which are attached in this line in this manner to masses m1 and m2, which are free to roll on the surface, and then we assume that everything is frictionless, so there are no energy losses on friction. Well, so I'm sure that most of you are familiar with the physics of how to set up systems of equations. Maybe from high school physics class, you basically need to draw the forces diagrams on each of the masses, and then apply the Hooke's law, right? So that the force, which is with which the spring is acts on the mass, right, is equal to negative k with the corresponding k times the displacement of the corresponding mass. So here x1 of t is the displacement of the first mass relatively to the equilibrium, right? And similarly, kx2 is the displacement of the second mass relative to its equilibrium. And so if you work out the algebra, sort of the forces diagrams, and then you can write this system of equations for these two masses. So again, so in this case, these are linear systems of equations. So systems of linear ODEs arise, for example, in questions involving springs attached to one another, complicated mechanical systems overall, currents, electric currents with resistors, inductors, and capacitors, chemical processes not away from equilibrium when there's some dynamics going on, then population models, and of course many more, right? So pretty much it's literally everywhere. So stocks market, prices, fluctuations, everything. So like that should be convincing enough that you should know how to solve differential equations and understand them. So we can also think of the nth order linear ODE we can turn it into a system of first order linear ODEs, right? So we can essentially by introducing new functions, right, and packaging them in a vector function. So the second order linear ODE y double prime minus ty is equal to 0 is equivalent to these two equations. Y prime is equal to z, so z is the new function whose derivative is equal to ty, which you can write down in the matrix form using this sort of off-diagonal matrix with components 1 and t, right, which multiplies the vector, the column vector y and z, and on the left we have the derivative of this column vector. So for that matter, any system of linear ODEs can be written as a first order system by introducing variables which take place in the high derivatives. So like similar system to what we saw in the springs problem. Well, although here there's some first order derivatives which would, so in physics, it will account for some velocities, right? So for example, if you study motion of particles in the presence of forces which are proportional to velocities, like air friction, for example, in certain range of velocities, that would be the case, right? So in this case, what do we do? Well, we just introduce in two new functions. Let's call them y1 and y2, which play the roles of derivatives x1 prime and x2 prime. And here we go. Right? So that's the first two equations would simply state that fact that we have substituted those derivatives with new functions. And then the other two equations would be purely algebraic on the right-hand side. So there are no derivatives on the right. So yeah, so you can try it yourself. Like write this as a first order system of ODEs, and then write the corresponding 4x4 matrix in the right-hand side. Okay, so then another exercise, take this third order differential equation with all coefficients equals to 1 and write it as the first order system. Well, that's the answer. So see here, that's the interesting structure of the matrix on the right-hand side. So as you can see, if you can move all these derivatives, y double prime, y prime, and y to the right-hand side, so you'll have y triple prime is equal to negative sum of these three guys. And then if we denote them with a, so yes, basically that's why the the second line is the second line, excuse me, the third row of the matrix is -1, and this 1 and 1 of diagonal, they show you that you introduce a new notation. So this is y, well, y prime, y double prime. Okay. So we did not rename the derivatives, which is common practice, but of course, like in a sense, we skipped the step. So you could have said that first we introduced the so this is y, this is say, let's call it y1, y2, and y3, and then so the fact that we have 1 here corresponds to saying that that the y prime is y1 prime is equal to y2, and this one corresponds to the fact that y2 prime is equal to y3. But sort of it's kind of, it saves you one step. There is a so-called normal form of the system of linear ODEs. So take which you can, it looks like this, right? So there's a vector function v, and there's a derivative d over dt acting on v, and on the right we have a of t multiplied by the vector function v plus some vector function f of t, which does not depend on the unknown functions. A is the matrix, which depends on t, and f is the is a certain function. So this is so-called normal form, and it is homogeneous when there is no additional function, when f of t is equal to 0. So again, we can talk about existence and uniqueness as we did previously for ordinary differential equations. So for any continuous matrix function, right? So you have a matrix worth of functions, and then every function in that matrix is continuous. And then every function in this vector function, both f of t is also continuous. So if all of those, n times n plus 1 functions are continuous at any time t0, we'll call it time, but you don't have to, so in the parameter t0, at any given vector v0 inside Rn, then this equation has a unique solution. With the initial value condition that v of t0 is equal to some given constant vector v of 0. Equivalently, so we can formulate this statement more algebraically. So for any fixed number s, the following linear morphism is an isomorphism, right? So there's a evaluation map if s from space of solutions to Rn, which assigns the vector to its value at x equals at t is equal to s, right? So therefore, and it's an isomorphism in the sense of linear algebra. Okay, let's now talk about the Wronskian in this context. Now, again, algebraic language is very convenient. So if you have vectors v1 through vn, the collection of n solutions of system of n linear ODEs, then you have an isomorphism evaluation at s of the span of vectors v1 through vn to the span of vectors of the same vectors evaluated at point s, which works like this. So this is isomorphism for every s. In particular, these VIs span the solution space if and only if VIs of S span Rn, which happens if and only if the determinant of the matrix, which is formed by columns of VI of S is equal to non-zero, is non-zero. So you write down those vectors, put them into the matrix, and then this will give you the Wronskian. Wronskian determinant of the corresponding system of equations. So let's look at an example. So you have a homogeneous system. V prime is equal to A of t times V. So we collect the basis for the solution space into a matrix, big V of t, whose columns are little VIs, right? Those vectors. And then well, such that the matrix satisfies the matrix equation. So here, V of t is also an n by n matrix, and then if like this is the, so this matrix equation is equivalent to is equivalent to n equations of this form, where instead of V we substitute the basis of solutions, right? So yeah, because of which column does, and also conversely, any matrix satisfying the above equation has columns which satisfy the vector equation. Now, let's talk about the fundamental matrix. So we have a matrix V of t satisfying this matrix equation. By the existence and uniqueness theorem, the following statements are equivalent. Columns of big V of t are linearly independent as vector-valued functions. Columns of V of t are linearly dependent as vectors for some value of t. The determinant of V of t never vanishes. For there is no value of t in the domain where we're studying the differential equation where the determinant is equal to 0. Or equivalently, you can say that the determinant of v is non-zero for some, just for some particular value of t. So this matrix V of t is called the fundamental matrix for the system of differential equations, or system of fundamental solutions, so just fundamental matrix for the system. So make sure you understand that all these four statements follow directly from this existence and uniqueness theorem, which we have discussed previously on previous slides using algebraic approach. So take this system of equations, vector, three-component vector x prime is equal to A, this 3 by 3 matrix, acting on vector x of t. So, well, let's check that. So in a sense, since we already kind of have an intuition of how the equation should work, let's check that this matrix capital X, which is filled with this elements, exponential functions of 3t and negative 3t, is a fundamental matrix. In other words, this first column, E3t, 0, E3t is a solution. Second column is a solution, and the third column is a solution. And these are the three fundamental vector functions, which are solutions of this system of ODEs. So there are two things to check. So that these columns are actually solutions, so that this statement is true, or you can just check matrix equality directly, that's fine as well. And second, that the columns are linearly independent, right? Because of course, if you take a solution and then you multiply it by a constant, it still will be a solution, but it's not going to be a different solution. So, well, let's just take the derivative of the let's take the derivative of this each component of the matrix. So we'll get these coefficients. Number 3 will pop out in front. And you just need to multiply this the matrix A by X. And it will be equal to, well, what is expected, right? So you can see that these matrices are equal, therefore the solution is this matrix capital X is indeed the its columns are solutions of the differential equation, of the system of differential equations. So we know that this is true, and now we need to show that those columns are linearly dependent. And as we just discussed, it suffices to show this only at some given value of t, and it's, well, the most obvious value of t to substitute is t is equal to 0. So then matrix X of 0 is a particularly easy form, from where it's more or less clear that it's invertible. So there's all these columns are linearly independent. So if you like, you can compute determinant, or you can do the row reduction. So that's therefore X of t is a fundamental matrix of solutions. Okay, do some more exercises by yourself, and also do the homework. So if the matrix A is a 2 by 2 matrix, 2 minus 1, 3 minus 2, then this is the fundamental matrix of solutions. Now, what can we, if say we have computed the fundamental matrix, how can we use it? So suppose we know that this, suppose we know a fundamental matrix for an equation, capital V prime is equal to A of t times V of t. And now we want to solve the initial value problem subject to initial condition, vector function V of t0 is equal to V of 0. Now, because V is a fundamental matrix, any solution is a linear combination of its columns. That is, it takes value of the form. So we take a constant vector C formed with the coefficients and then arbitrary coefficients, and then we multiply it on the left by the matrix V of t. So we want to find V of t such that it's, if we evaluate it at t0, we'll get V0. So V bold V of t0 is equal to capital V of t0, the matrix, multiplied by the coefficient vector C. So this is equal to V0. So if this is the case, we can, and we know that matrix is invertible, right? We can just compute the sought coefficients like this, and therefore that would provide us with the explicit answer for the solution for the initial value problem, right? Because we know that V of t0 is equal to V0, right? So we know that the yes, we know that the solution is equal to this combination. So and we just substitute the answer for C. So vector V is equal to this combination. So we take, and you can see that the answer checks out. If you plug in t is equal to t0, then V times capital V inverse cancel each other. They become an identity matrix, and it is consistent. So let's do an example. The 2 by 2 matrix 2 minus 1, 3 minus 2. We have checked previously that this 2 by 2 matrix e to the t, e to the minus t, e to the t3, e to the negative t is the fundamental matrix. And then say you want to solve the initial value problem for x of t with x of 0 is equal to 1, 2. It's a vector with components of 1 and 2. And therefore, we can readily write down the answer. So this is the capital X of t times capital X of 0 inverse acting on x of 0. So we get the 2 by 2 matrix acting on times x 0 inverse times vector 1, 2. Which is by now should be an easy exercise for you. So you invert the matrix, it gets you 3 and 1 switch places. You need to negate the off-diagonal elements, divide everything by the determinant, which is 2, and then you do the computation. So eventually you get 1/2 times e to the t plus e to the negative t, and e to the t plus 3 e to the negative t. So now you can try it by yourself with our first example of the 3 by 3 matrix. So assuming that we know the fundamental matrix X, solve the initial value problem, which satisfies X prime is equal to AX of t with this initial condition that X of 0 is equal to 1, 2, and 3.